All right. Um, so yeah, today we've got 2 pages of homework to do, and that they're actually due on Thursday. You have your exam on Thursday, so you're gonna have to submit this before the exam. All right. Um, the material that we're talking about today is primarily L'Hopital's rule. So I guess I'll do a brief refresher on what that is. Let's move over to the right-hand side. Okay, so L'Hopital's says that if you have a limit that ends up being of the form 0 over 0 or infinity over infinity, you can have a plus or minus, then you, and I guess I should say specifically that the limit should be something like a function fx over a function g of x, limit as x goes to anything, really. If you have a limit of this form, and if you try to evaluate it, it gives you one of these two types, then what you can do is you can say that this is equal to the limit of, and then there's this special thing here, not a, but x, where what you do is you take the derivatives of the upper function and the lower function and you construct a new limit out of that. The important thing is that this is not the quotient rule, obviously. Okay, this is only a technique that you can apply to specific kinds of limits as long as they satisfy this kind of type condition. So if you have this happen, then you can actually say that these two limits are equal, and hopefully by taking the derivatives of the upper and lower functions, this simplifies the overall limit so that you get to something that you can actually evaluate. It's also always possible that you might be able to, or you might need to use L'Hopital's more than once, but every single time that you try to use it, you have to check whether or not the limit is of one of these forms. Then the other thing I should say is something about indeterminate forms as a whole. So indeterminate forms, the first two are the 0 over 0 and the infinity over infinity. So by definition, indeterminate forms are these special forms that you don't know right away what their value is. In fact, their value actually depends on the context, specifically on what functions you're dealing with, because they'll give you different values in different situations. So we have these two. And then another form that you'll see is 0 times infinity. What's important to notice is that you can actually go from 0 times infinity to either of these two. All you need to do is reciprocate one of them. So if you reciprocate the infinity, you're going to get a 0 in the denominator, because 1 over infinity is equal to 0. And if you were to reciprocate the 0, 1 over 0 is kind of an infinity, and so you get infinity over infinity. So they'll be reciprocating as reciprocating will be one of the transformations that you do in order to make your limit get into this form. So you'll be able to use L'Hopital. So you'll see that on, I think, problems on the second page. Some other forms I want you to be aware of are, I have to try to remember, I think infinity to 0 is one of them. I think 1 to the infinity, and I think also 0 to the 0. Yeah, maybe 0 to the 0 to the x. Yeah, I'm. Yeah, that's right. That's right. Yeah, and so the thing is that this you do by reciprocating. To go from any of these three, you can actually get to the 0 times infinity through taking the logarithm. So you can just say, like, you apply the log function to it, and then in each one of these, you're going to end up it's going to transform the value into 0 times infinity type, and we'll see that with actual problems as well. And I think there's just one last version, which is kind of an outlier. It's infinity minus infinity. And so this is also an indeterminate form, can hold multiple values. Usually, this infinity minus infinity shows up when you actually have two fractions that are being subtracted, and then what you do is you combine them over one denominator. But there's not really a standard strategy, so it doesn't quite fit into this structure that I'm depicting. Okay, now let's go ahead and work through the problems. So for number one, well, I guess the overall idea is we should probably use L'Hopital's, but before we do that, we should check that we can use L'Hopital's. So if I check mentally that I plug h equals 0 in, I would get a 0 on top. I'd get 3 squared minus 3 squared, so 0 on top and 0 on the bottom. So therefore, I can use L'Hopital's. And anytime that you are trying to use L'Hopital's, say like on the exam, you should make sure that you somewhere indicate that you calculated what the actual value, or like, yeah, calculate a 0 over 0 or infinity over infinity. You have to make sure that you actually can apply L'Hopital's. We check that you actually do verify this, because otherwise it really is a problem. Like, thing is, like, if you can't apply L'Hopital's but you do, there's a very high chance that you're gonna get the wrong answer. So this verification is important. Okay, well, let's go ahead and calculate this. So we would take the derivative of the numerator. So that's going to give me a 2 times 3 plus h on top, and then a 1 on the bottom. And so I can just plug in and I'll get 6 if I plug in. And this should match up with this. So basically, this is just going from here to here is just recalling the limit definition of derivative. And so you can just do a quick confirmation that that is actually the correct value. I'm not going to bother with that because it's only a bonus. Okay, for B, well, you can see that if I plug in pi over 2 to here, the numerator is going to be 0 and the denominator is going to be 0, so I can use L'Hopital's. And sometimes I'll put a LH above my equal sign to indicate that I'm applying L'Hopital's for that step. Okay, now derivative of cosine is negative sine of theta, and that's, okay, the numerator. The denominator is just going to be 1. Okay, so I just get negative sine of pi over 2, and then if we think about this, pi over 2 is negative 1. It's going to be negative 1. Yeah. Okay. Any questions so far? Okay. Okay, got a thumbs up. Good. All right, so number 3, let's see. Well, we still keep going, but all right, so first we check, can we use L'Hopital's? I plug in, I'll get sine of 0, which is 0, divided by 0. Yes, I can use L'Hopital's. Great. So we go ahead and use it. Theta goes to 0. I have to take the derivative of the top. That's going to be a cosine of theta squared, and then there's a chain rule times 2 theta divided by, and then denominator is going to be a 2 theta. Okay, so that's interesting because those two will cancel. And then I can just take the limit of the result. That's going to be cosine of 0, which is 1. Oops. All right. D looks like it might use more than one derivative. Okay. So, yeah, for this one, we try plugging in. We'll get infinity on top, and we'll get infinity on the bottom, which is also an indeterminate form, so we can still use the L'Hopital's. Limit as x goes to infinity, derivative of the top, 6x plus 8. Derivative of the bottom is e to the x, right? But if we try to directly plug in, we're going to get infinity over infinity. Okay, so I'm still forced to use L'Hopital's. Just put that below. So I'm using L'Hopital's again. And derivative of the numerator is 6. derivative of the denominator is e to the x. And then here I can plug in. So if I plug in this time, I'm going to get 6 over infinity, which is 0, dividing by an extremely large number. Okay. Okay. Any questions on any of this?
When it says your answer should match and then it tells you, what is that exactly telling you?
In a way, it's just explaining that this limit can come about naturally from somewhere. So these are both like saying like, oh, that this limit is coming from a particular limit definition of derivative. It's the other one, the one that we don't usually use. Whereas this first problem, it's using the standard limit definition of derivative. So like this limit calculates this derivative, and this limit calculates this derivative. Another thing you can do is you can actually just compute and check that your calculation for the limit should match the actual calculation. So for example, with number 1, we could just check, like take the derivative of that function. You're going to get 2x, evaluate at x equals 3, which then is going to be equal to 6. So you can confirm that like these two things match with each other. It's just kind of just to say like, oh, where did this random question come from? It came from a derivative. Okay. So hopefully that answered that. Any other questions? No? Okay. All right. Yeah. I mean, the verification I would say is optional. Like, I don't think it really shows you very much. You can go ahead and do it, but I don't really think it's necessary. Okay, and then we have only 4 more problems here. Okay, it's gonna be a bit short. Let's see. All right, so for this, I would try to plug in and see like what type of expression we get. So if we were to just naively plug this in, we would get 0 times negative infinity, which is effectively a 0 times infinity situation. And well, that's not directly matching the the format for L'Hopital's, but we can make it match the format for L'Hopital's if we just reciprocate one of the functions. And in this particular case, there should be one, you should kind of know like which function to put into the denominator. There's only one good choice, which is going to be the x squared, right? If you were to put the ln, it would kind of make things way too messy. So you really want to. So what I'm doing right now is I'm just rewriting. We're gonna leave the ln of x on top, but we're going to put the x squared into the denominator, and I'm going to use a negative exponent because the next thing I'm going to do is take a derivative. What you can do here is you can just double check also like that this is the correct indeterminate form type. So if you plug in, you're going to get infinity for the numerator, infinity for the denominator. And so, yeah, we can use L'Hopital's. And let's see. So ln of x is going to give me 1 over x. And this x to the negative second is going to give me negative 2x to the negative third. And then we can just try to clean this up a bit. Using algebra, let's see, if I bring this on top, I'm going to have a negative 1/2 x squared, right? So if I just do algebra, yeah. And so now I can plug in and I'm going to get 0. So the final answer for this is 0. Okay, for f, we see that if we directly plug in, we'll get 1 to the infinity. All right, so this is where we need a slightly different technique, I would say, because this is like of the exponential form. Like you have a base and an exponent, and you want to lower that exponent down by using the log function. So there's a sort of a technique that uses there's a technique where what we do is we set the original problem to be equal to some value L. And then we just take the logarithm of both sides. The reason to do this is it just helps to kind of break the problem into pieces. I know that some people, they like to teach this as rewriting this with like exponential of a logarithm or something. And the when you do it that way, I feel that the working gets to be a bit convoluted. It just looks a little bit messier to me. But I mean, if you're more comfortable with that approach, you can do that. I don't know, maybe I can show the other way. But here we're just going to take the logarithm. So ln of L, and then I'm going to take the logarithm of the problem. And I know that I can push the log into the limit. So I'm going to have limit as x goes to infinity. The log is going to pull the x out, and then I'm going to have x times ln of, and then the stuff in parentheses. Okay, so this was me taking logarithm of both sides. And at this stage, we have an infinity times a 0. Okay, so we're closer, but we need to do a little bit more in order to make this work. So we need to put something into the denominator, and again, it makes more sense to leave the ln on top, so we bring the x to the denominator. So I'm going to have ln of 1 minus 2 over x on top, and I've got x to negative 1 on the bottom. And here we can just check that we have a 0 over 0 type at this stage. So I can use L'Hopital's. All right. So now derivative looks a little bit convoluted, but we have to do it this way pretty much. Let's see. This is going to become 2 over x squared, taking the chain rule. And then this is negative x to the negative second. Yeah. And so now I'm trying to simplify this mentally. So we can pretend that we multiply top and bottom by x squared, and that cancel both of these. We can pull that out. Let's see. So I have a negative 2 divided by 1 minus 2 over x. And I think I can plug it. Yeah, I can plug it in. Great, so I get negative 2. Okay. But the thing is that I'm not done yet, because notice what our first statement was in this whole chain of equalities. We have ln of L is equal to negative 2. So what we found is ln of L is equal to negative 2. And what we need to do is to recover the value of L. We need to get back to the original problem that we're trying to find. So the way we do that is we exponentiate both sides. We will end up with L is equal to e to the negative 2. And we can't simplify that anymore, so this is the answer. Okay. Did that process make sense?
Yeah.
Okay, great. Yeah. I wonder if I don't know if Spencer did it things in the other way or not. It's actually harder to see it. I mean, I'm debating whether or not I should show the other approach or not. I'll say something about it, but I don't like it. So I'm just looking at like the other problem where it just has x to the x, just for simplicity. So there's a special property that the exponential and logarithm functions have, right? We know that they're inverse functions. Craig did it the same way I did. Okay, right. Just in case like you ever come across this though, I'll mention this because I know that some people, for some reason, they explain this, and I mean it's fine. It's just that it is a bit, I don't know, more cluttered. It's more cluttered. So one way that people will avoid doing this, like this kind of approach, I would say this is more of like creating a sub problem, solving the sub problem, and then coming back to the original problem. So like defining L and then taking the log, that's sort of like you're constructing the sub problem involving the ln of L. But some people, they don't even want to introduce that new variable. Instead, they just want to kind of, they can avoid that by doing something slightly clever-ish. So like say you had like this limit as x goes to whatever this is doing. So x goes to 0 in this case. One thing that they'll do is they'll use this special property that exponential and log cancel each other and that you can nest them in this way. The reason is because you can then lift everything into the exponent of e, where you then have a log. So like this is all one step. This is all just one algebraic step. E to the ln of x to the x. This is the same statement, for example. And then what they would do is they would just apply the property that log has where it will pull the thing out. So then they would do that, and then they would finally push the limit into the exponential. So then you end up with this mess. So then it's x times ln of x. And so in this way, it's like you end up getting a subproblem that shows up in the exponent. And then, you know, depending on the preference of whoever's like teaching it or writing up the solution, you could either, you know, pick into that particular subproblem, just like get rid of that exponential in the base, or you would just write everything with the e in the base. You're always working in the exponent, and it just looks messy to me. But some people will legit write textbook solutions in this style. So I wanted to at least mention that in case you come across it. All right. But let's go through this in the what I would say is the typical fashion. Let this guy be L. Well, first of all, we know this is 0 to the 0. This is an indeterminate form with like an exponential kind of thing. So you need to take a logarithm. So we set the whole problem equal to L. We take the logarithm of both sides. And so then we would take the logarithm of the x raised to the x. That's going to lower the exponent. And so we have that, right? This is our subproblem that we're trying to solve for. And right now, this is of type 0 times infinity. So I need to get it into a format so I can use L'Hopital's. So I'm going to need to reciprocate something. And the only thing that makes sense to reciprocate here is, again, the x. It's not the ln of x. So go ahead and do that. Okay. And now we take a derivative. Or well, not a derivative. We apply L'Hopital's. I should be more careful with my words. So 1 over x on top minus x to the negative second on the bottom. And now we can clean this up if you just imagine, say, multiplying top and bottom by x squared. That's an easier way of thinking about rearranging the exponents. So you get negative x, I think. I wrote something kind of messy there. But yeah, negative x. Okay, so limit of negative x, that's going to be 0. But remember what problem we are solving at this moment in time, right? So this is always like the most common mistake. Like you end up thinking that what you're doing is solving for the original problem, but instead you're actually solving the sub problem. So you always need to like double check yourself when you do this kind of thing. Double check if you're solving the original problem or the sub problem. Here we're solving the sub problem. ln of L is equal to 0. So therefore, L is equal to e to the 0. And for this guy, I really want you to know that e to the 0 is 1. I see, it always irritates me whenever I see someone write e to the 0, because that's just 1, and basically it's just saying that you don't know that simple fact. Okay. All right. So hopefully that's fine. Everyone is following. Last one we've got is h. So h, I think, is also slightly, it's messy algebraically, I think, just a little bit. But it's also interesting in that regard, because this is actually one of the more challenging versions that I've seen. So if you just do a quick check on what this is, right? Whenever you encounter a limit, you should always start by trying to plug it and see whether or not you're able to. So you don't want to overcomplicate a problem. But here we would end up with 1 1 over 0, which is infinity, and then 1 over 0, so another infinity. So we end up with an infinity minus infinity situation. Okay. Well, but you see also that we've got these fractions. Well, the only thing that we could possibly do to this at this point is to combine the two fractions and see what we get. Right. You definitely can't apply L'Hopital's at this stage. Remember, it only applies to a fraction f of x over g of x. It only applies in such a circumstance. It's very restricted. Let's see. So x minus 1 minus ln of x over x minus 1 times ln of x. Okay. So all I did was I subtracted the two fractions. Hopefully you followed that. I put them over a common denominator and then I did that. All right, so we just subtracted fractions there. And let's see, if I were to plug in 0 minus 0, maybe I'll just put the little calculation, maybe I'll put it on top. So if we plug it on, we would get 0 minus 0 over 0 times 0. Okay, so 0 times 0 is actually totally fine. So we like arithmetic still makes sense for 0 times 0. It's only 0 times infinity. That's the weird one. So this, we end up with a 0 over 0 situation, which means we can use L'Hopital's at this stage. So go ahead and try that, since that's really the only thing we can do. Okay, and when we do that, we're going to get a 1 minus 1 over x on top. And then on the bottom, we have a product rule. X. Well, if I got this. Derivative of x minus 1 is just 1, so it's ln of x here, and then plus x minus 1 over x. Yeah. Okay, now can we plug into this? Well, doesn't look like it. Yeah, no. If we try to plug into this, we're going to get 1 minus 1 on top, and we're going to get a 0 plus 0. So we end up with a 0 over 0. So we still have an indeterminate form, but we have a good one that we can we have a form that isn't a number, but it's an indeterminate form. And so we can actually use L'Hopital's again for this. Okay. Okay, so we try to take the derivative again, and I think, okay, yeah, so I'm gonna do something clever for that, but the numerator, this has a minus. If I take another derivative, it'll give me another minus and it'll be squared. So I know it's gonna be this. For the ln, I know that becomes 1 over x. But now for this guy, what I want to do is I want to rewrite this so that it's easier to take the derivative of. I really don't want to do quotient rule. And thankfully here, if I just do an algebraic thing, I can avoid it. So I just rewrite it. 1 minus 1 over x. Okay. And with that now I can just take the derivative. This is going to be 1 over 1 plus x squared. Or I wrote it, I said it wrong, but I wrote it correctly. Just take the derivative of that. Okay, and then here we can finally plug in. So if I plug in, I get 1 on top, and I'm going to get 2 on the bottom. And then if we just trace through, we'll see like we solved the original problem. This wasn't solving for ln of L, so we can just box this answer. Okay. Questions on anything? Yeah. Okay. Well, I'll stop the recording.